videos, I guess, or shorter videos. Okay, Tristan, now you can ask the question.
I was wondering what else is needed for the Moon project other than the journal entries
Not
for the fully online students?
right now, nothing. So first you have to do your observations, document that you're looking now at these changes of the angle between the moon and the sun. And then at the end, you're going to fill out that worksheet that I posted. So let me share the screen with you, and then I can show you on the Blackboard, okay?
Hmm.
How's this week for you? Good?
Yeah, this week is good, but the last week's quiz kind of hurt me.
Okay, good. So let me show you. What was it? The Moon Project. Okay, so here is the link for the Moon Project.
Yeah.
Okay, see this Moon Project F16, this link over here? This
Hmm.
is eventually what you will need to fill out. So if you want, you can print this and have it there, because I do ask you to document few days when you were observing the moon, and what was the time and what was the location and how high it was above the horizon.
Is the altitude like the degree?
The altitude is actually like the height above the horizon. How high is it above the horizon?
Ah, okay.
Yeah, and then you have but as you can see, you should answer these questions towards the end of your project, but you can maybe just pay attention to some of these facts so that it's easier for you to then summarize that when you're done.
Oh, and for the observations, does it matter if we do it like the day after we just did one, or do they have to be 3 days apart?
No, does not matter, but it does matter that you kind of observe as much as you can of one cycle.
Ah,
So,
cool,
so
cool.
don't do one observation and then next one, and then just don't even attempt to do it for the whole week. I sometimes get it's not actually easy to see the moon, especially if it's cloudy or whatever. But so
Yeah.
whenever you can, then just make one observations. Can I take a look at your journal?
Oh yeah, sure.
Do,
Please.
do you
That'd
have
be
some
awesome.
entries?
Yeah.
Okay. Well, actually, there are 5 of you that are doing the moon project.
Is
Okay. So let's say the first week. You said the phase of the moon was waxing crescent and was about 45 degrees from the sun. And how did you measure this?
with the hand signals, I guess.
Pointing one hand, like one arm or a hand at the moon, and then the other one at the sun, and then just trying to get the angle between them.
Yeah.
Perfect. Did you see the moon now tonight?
I haven't actually looked
It's
out
actually
tonight.
really nice. I maybe 1 hour ago I came inside, and the moon is pretty high above the horizon, and it's a nice quarter moon.
Awesome. I'll probably do a entry tonight.
Yeah, exactly. You can get the moon tonight. Okay, so let me see then. So that was one entry you had last week. So last week you started, and then you have the phase of the moon was a waxing crescent, was about 51. Okay, so see, one of these measurements wasn't really correct.
Mm-mm.
And maybe it was your first measurement on Saturday. Probably it was a smaller angle.
Yeah.
Tuesday, this was 3 days ago, right?
Hmm.
51 degree. That would make sense, because now, if you now go outside, you should
Yeah.
get approximately 90 degrees, right? Because
Oh,
now,
because it's higher.
yeah, now you don't see the sun. The sun has set below the horizon. But did you see? I have a hint how you can estimate how far below the horizon the sun is. So you know what you could do? You could measure the altitude of the moon from the western horizon. So just think where is the ocean, what direction, and then have one hand towards the ocean, and then measure the angle of that hand and the one pointed at the moon. Okay, so that should
Oh, okay.
give you less than 90 degrees for sure. And
Yeah.
then estimate how far below the western horizon went the sun. And if you checked when the sunset was, I think every hour after the sunset, the sun goes 15 degrees below the horizon. So let's say it's 2 hours after the sunset, the sun is 30 degrees below the western horizon. And so then you can add those two angles and get basically the angle between the moon and the sun.
Ah, I see.
Okay, so
Okay.
here is what I just said. It's always easier to draw.
Yeah.
So this is, let's say, the western horizon, and
Mhm.
I don't know. Let's say the sun has set 2 hours ago. So the sun is here, 30 degrees
Yeah.
below the western horizon. You don't see it. It's dark now. Okay, but you go outside and you find the quarter moon,
Yeah.
basically something like this. Okay, so
And
then
then
you
add
can measure
those.
this angle over here. Get
Uh-huh.
degrees, add these two angles, and that's your 90-degree angle between the moon and the sun.
Ah, I see. I see.
Does
Sounds
that
good.
help?
Yeah, that makes sense.
Okay, very good.
Because it
Do
was
you,
saying it was harder at night to get the angle.
I don't know. Depends. I generally think, it's hard to measure these angles, but I'm not going after like 1 degree precision. It's
Yeah.
good as long as you can see like, that the angle is less than 90 degrees or more than 90 degrees, right? And that's pretty easy to see.
Yeah, definitely.
Good. And I think usually we honestly, like, I think I said that, so I don't want to repeat myself, but before I came to grad school in US, I never even paid attention to the moon, even though I got like my undergraduate degree in astrophysics. But then like,
Yeah.
I was asked to teach these two projects to students, like, that were undergrad. And then I thought like, wow, this is like so awesome. I've never noticed this, but there is like so much change in the sky. So then I
Yeah.
asked like all students to do this just to see like, how the sky really changes.
Yeah, with actually like observing it in real life.
Yes. Yeah, so really don't stress. Don't stress too much about the precision. Just like try to go every few days and just like notice really how much change there is between the sun and the moon, and then document that in your journal, and you should be fine.
All right, and will you tell us at what point we're done observing, or?
Okay, good. So let's say for you need like approximately this is what you need. You need to document as much as you can of this like motion of the moon. So once
Mhm.
you let's say you started, I think you said waxing crescent, something
Yeah.
here. So if you now go and now you're let's say at this position over here, it's the quarter. So you need like 1, 2, 3 more weeks and you're done.
Ah, okay.
And you're not going to be able to see the moon over here. So probably like 2.5 more weeks for the moon to come here, and then you can stop. Unless you want to go like another week to come back to where you started.
All right. So we're just doing the observations, and then after that, we fill out the worksheet.
Yes.
All right, cool.
And you get 6% of your grade, which is a lot.
Yeah, I can make it or break it.
Yeah, good, good. Okay, so really no questions about gravity. That was easy.
Oh, actually, yeah, I had a few.
Okay, very good. I would like because it's not super easy. I think it's different kind of a challenge. It's not anymore like 3D thinking, but there is like some
Yeah,
math
I
over there that it's not that easy.
I like this more because it's like more straightforward than like being oriented the right way.
I know. I feel bad for students, like, because it's like so hard for the second and the third week with all of this like brain torture, thinking 3D and all of that. But we
Yeah,
are done with that, so it's gonna change now completely.
awesome. Yeah, I
Good.
was I was thinking like astronomy and physics kind of go hand in hand.
Yeah, no, that's true. Like as an undergraduate student, you would get your basically major in physics, and then you can just like minor if you want in astronomy, and that would mean like you take, I think 3 or 4 upper division courses in
Mhm.
astronomy. Let's say if you're at UCSD, and that's it.
Yeah,
Then you can go like to a PhD program where still the physics is like the majority, and then just like you can do your dissertation in astronomy.
that's awesome.
It's very nice. Yeah, if you want any more advice about career, stop by. I can talk to you.
Cool.
Okay. So which ones? Was it homework or a gravity worksheet that you had question?
The homework quiz or
The
the
home. The.
homework.
Which one?
Um, I think it was just a quiz.
Oh, I
I don't.
cannot go through the. But no, no. But I can help you with
Yeah.
the
If I could
files.
describe it, I think it was.
Well, this one is pretty hard. Okay. What did you do here?
Um, you want me to answer it?
Yeah, yeah, yeah. Just
Okay.
tell me, like, so the question is basically what's the net force, right? By
By the
this
greatest.
middle asteroid. Yeah. So first of
Oh,
all, what does that mean, the net force?
the total gravity acting upon it, I think.
Uh-huh. But okay, here is the trick, right? The gravity is always attractive force, which means this little asteroid on the right side wants to pull this big one in the middle towards itself, right?
Mm-hmm.
And then this asteroid over here also wants to pull the middle asteroid basically towards itself. And because this one has more mass and they're
It's
at the
gonna.
same distance, it's going to pull more. You agree with that?
Yeah, definitely.
Okay, so now the net force, and that's where students make mistakes sometimes, is not really you add them up, but it's more like you subtract them, right?
Yes.
Okay, so you need to find the difference of these two forces to get the net force. And I can help you kind of, the net force will be something like this. The force in this direction towards this asteroid. Not really, okay, wait, I have to be really precise. Okay, so here is the net force would be something like this, okay? So the difference between this stronger pull and then minus this pull towards this asteroid. You agree with that?
Yeah. Is there like a formula for that, or is it just?
So usually, well, here I think you have to do calculations because not all of them are at the same distances, right? So yes, you
Yeah.
do have formula. You know the force of gravity between, let's say, A and this asteroid on the left side. What's the formula there?
I also had a question about the formula too. Isn't the formula here, going back to your lecture, the PDF? I had a question. Let me go down to the formula.
Uh-huh.
Um, oh, here it is. So it's that mass one times mass two divided by distance squared.
Yes, and you can ignore that. There is that G gravitational constant there, but you can ignore that for the homework, okay? So it's just like force is going to be like, mass one, and then this pencil is horrible for writing. I have to buy something else. And then
Yeah.
distance squared, okay?
Mm-hmm.
Love.
My question was, now I fully get it.
Okay,
I'm only calculating like the one side at one time, correct?
exactly. And then the other side, right?
Okay, that's
And
what was
then the other
missing.
side, and then you find the difference between
I
them.
For some reason I thought it was like both of the asteroids going towards the middle for some reason. I That was clearly wrong. But what it's meaning is one side is pulling more than the other side, and you just calculate each individual side.
Yes, and then make a difference, right?
Yeah, so the M equals 5 on the left side would be the first M1, and then the M2 would be 10
Yes, the middle one.
divided by the one distance. That's what was messing me up because I was thinking, do I add up the both distances and then square it? But we're only talking now about one side more than the
Yes.
other.
I
Ah.
actually I can tell you like analogy. The very good analogy to this would be like imagine like you're standing and you spread like your arms apart,
Mhm.
and then you have two friends like they're pulling on your arms. Okay, that's what this like middle asteroid is feeling, right? Both of these like asteroids on a side are pulling on that asteroid. Like when they're pulling on
Yeah.
your arms, you have contact, but the gravity doesn't need really contact. Okay, it's like a long range force. So, anyways, now let's say what could happen to you if those two friends are pulling. Well, depends if they're pulling with different forces or like the same forces. If they're pulling with the same forces, what will happen to you?
They cancel each other out.
Exactly. And they don't cancel each other if you add them up, but you have to subtract them, right? And so
Yeah.
then they cancel each other and nothing happens to you. In this case, clearly, this one is pulling more. So that means they're not really going to cancel each other, but the net force will be in that direction. So for you, that would be like one friend pulls more. So you would move towards that friend that pulls more, but
Hmm.
not as much as he pulls, but how much he pulls minus what the other person pulls, right?
Yes. And that's the definition of net force.
Yes, exactly. That's the
Oh,
definition
that
of the
makes
net
sense.
force. Yes, very good. Good that you asked this question because this is hard. I know that students on campus will struggle with this.
I also had a question. Uh does A and B have a difference because B is elongated?
That's a very good point. No, because in physics, we always assume as if all of the mass is in the center. So the
Um,
fact that they have different shapes does not matter at all. You always assume all of the mass is in the center. And when we are looking at these two asteroids, we look, their distance is basically from one center to another center.
mm-hmm. I
You
see,
know,
I see.
good. When you're on the Earth as well, the force of gravity between you and the Earth is going to be like your mass, the Earth's mass, and then the distance of your feet from the center of the Earth, right? And that's the radius of the Earth. So again, we are assuming as if all of the mass of the Earth is in its center.
Yes, that makes sense.
Good.
Um, and I had a question. Um, the way we're like describing it is as if like the asteroid on the left is pulling. Wouldn't since the asteroid in the middle is bigger, wouldn't it be going towards it?
Well, I know. Sure, we don't know what's going on over here, right? Because
Yeah,
that's the same thing. Okay, think about sun and the earth. Like, wouldn't the earth go towards the sun because like, there is that force of gravity? Yes, if the earth didn't have the velocity that it has, right, or the speed that it has, basically to go around the sun and basically balance that gravity. So that's correct. Like you don't know what's happening over here. Are these like, little ones moving towards the bigger
yeah.
ones? Or they're in some kind of like, system where they maybe form together, so the little ones have enough speed basically to resist this gravity, right, and to move in some stable orbits.
Oh, okay. So like essentially it's just like there may be orbit you can't really tell. It's just
And it's not important kind of for this
yeah,
exercise, but I appreciate
exactly.
the fact that you're thinking about that. No,
Yeah.
no, really. Another thing is like, we launch the satellites in the orbit, right?
Mhm.
And how do we do that? I mean, we know like whatever you throw up in the air, it's going to come down because of the gravity. But the satellites are not going to come down because you will give them enough speed so that they can simply just like keep falling around the earth and not really fall onto the earth, right? So
Exactly.
you know when you have speed, you can kind of be in a stable orbit even when the gravity acts on you.
Awesome.
Good.
That's kind of like the ISS. It's like always falling.
Yes, exactly, exactly. Yes, I was giving that example in the classroom as well. And occasionally you need like a little bit boosters, right, to give it a little bit more speed because of the drag and all of that that it experiences. But exactly, they can go for a long time without basically any fuel as long as it keeps the speed, right, in the space.
Definitely. Should are we just gonna go through this whole thing or no?
Which one? That number five?
Yeah.
Oh, if you want. I thought you felt confident about that.
Oh, I do. I just want to like double check.
Yes,
Um,
no, and I think it's going to be useful for like, other students. Yeah. So I mean, as you said, right, you need to calculate force for these two, and then the force of these two, and then find the difference. And then you don't have to do that in the second pair because it's completely the same. They're the same masses, the same distances, only the difference is in the shape of these two, but that doesn't matter because all of the mass is in the center. But then
yeah.
here is these two are tricky, okay? So where is more force? That's what you need to figure out. What do you say actually, just by looking? Does let's say this system over here, will
Mm-hmm.
there be more force on this middle asteroid or in this system?
Um,
So A or
I
C?
think I think C
Why?
because the distance is shorter.
Yes, very good. So even in this case, you knew there was more force in this direction, but here there is even more because the distance is smaller. How about this one?
Um, compared to which one?
I don't know. C.
Oh, to C? Oh,
Uh-huh.
I would have to say D since there's a larger mass to the right.
I know, but the distances are larger, right?
Yeah.
So you have to calculate. Like, I don't know, you cannot really like eyeball it. You have to
No,
calculate
you can't.
this.
Yeah, it depends on the distance and the mass in the
Exactly.
calculation.
Exactly.
All
Exactly.
right. I think I did understand that one. Maybe could we scroll through like the worksheets and I think I remember which one I
No, I
got
can
wrong.
actually ask you one more, I think. I remember
Oh.
something that it's let's see, what was this number six? Oh, this was just simple. Okay, so
Oh
you can
yeah, that was
actually, if you
super
wanna,
simple.
do you wanna tell the answer to one of these, let's say, so that people can check on themselves if they're doing this correctly?
Yeah, let me see. The rank from greatest to the strength of the gravitational force exerted from the pairs. Wait, rank the okay. Oh, um, rank for, wait, sorry, I'm having a brain fart.
That's
Rank from the
okay.
greatest to the least, the strength of the gravitational force exerted between pairs of stars in cases A through D. So I just add up, and then this is just like the total gravitational force.
No, okay, wait. See this over case A. You have
Uh-huh.
one star that has this mass, and then you have another star that has this mass, and then you have distance between them.
Oh, I get it. There's two stars and there's just distance in between it.
And there is distance between them, right?
Yeah, and you just add up both of the masses and then
Oh, I cannot hear you right now. Are you there?
yes, am I here?
Oh, okay, okay. Yeah, so you
Okay.
basically, for gravity, you always need two objects with mass. So that's your
Exactly.
object one, object two, and then the distance between them. So how do you calculate the force of gravity that it's in this case A?
So mass 1 times mass 2, so that's 4 times 2 is 8, and then you square the distance.
Mm-hmm.
So that's 4. So 8 divided by 4 is 2.
Yes, that's it. Perfect. And then you do that for the pairs B, C, D, and then you get the numbers, and then you can compare the numbers, right? That's what you need to do
Yeah,
there. Okay, very good.
definitely. Yeah,
Good.
I got that one. I think it might have been gravity 5, maybe.
Gravity 5 was that one with 3, so we went through that.
Oh no, this one.
This one, okay. See,
Yeah.
I somehow know, maybe because I taught this for 40 times now. Okay, so I like this one. So this one is first asking you to compare the forces on the asteroid that's on left and then acceleration, okay, for the left asteroid. So these are the left asteroids, right?
Mm-hmm.
What do you see about left asteroids?
They're smaller? Or
Are they all the same?
exactly, yeah.
Yes. And then, okay, the next thing that is helpful when you're looking, you have now 4 pairs of asteroids. Are they all
Mm-hmm.
at the same distances with respect to each other?
Yes.
So that's perfect. So that helps you, right? Because you
Yeah.
don't even then have to consider the distance. You don't have to do any calculations here. You just have to look over here.
At the masses?
Exactly. So in which pair the asteroids feel the greatest force?
Um, D?
Because
Because the mass is so large,
exactly.
and then it
Exactly.
just goes down sequentially.
Exactly. Does that make
Oh,
sense? So
yeah,
if
yeah,
you
yeah,
if you were to
definitely.
calculate, you would get like, okay, 5 times 20, 100 divided by, 5 squared, 25, 4. So the force is 4 over here. The little one feels the force of 4. The big one feels the force of 4, right? And then you could
Uh-huh.
repeat that over here. You would get force of 2. Here you would get force of 1. Here you would get like, less than 1, okay?
Less than one, yeah.
Perfect. And now, so that's the first question, to rank the forces. So this one feels the greatest force. Now, the
Mm-hmm.
second question was like rank the accelerations of these asteroids on the left-hand side.
Rank the what?
Accelerations, I think, right? Was that
Oh, accelerations.
yeah, the accelerations.
Um,
First, tell me, what is the acceleration?
is any change in speed or velocity or direction?
Very good. And why would something have the acceleration? What needs to act on
Gravity?
that? Yes, okay. So if the force is acting on a mass, you agree, there is an
Yeah.
acceleration. So I don't know, like, how clear that is online, but I always like to think about second Newton's law, that the acceleration is like, force over mass. And what
Yeah.
this means, okay, what this means is like how much something will accelerate does depend how much force you apply on that, but it also depends on the mass of that object. Okay, so now think about it, like, I in the classroom I would tell this to students, like, I have a son, he's very skinny, like 35 pounds. Okay, so
Yeah.
imagine like I put my son in front of me and then I take like a sumo wrestler in front of me. Okay, so the sumo wrestler has like 10 times more mass than my son. If I push them with the same force, what will happen to them? Are they
The
going to react?
smaller one will, no, they'll react differently.
Exactly. They're going to react differently because they have different masses. The sumo wrestler, nothing happens to him. Maybe even like I bounce back, right, when I push on him. But my son might like, roll down the floor, basically, if I push like, if I
Yeah.
push like really hard. So, you apply the force, but how objects react to that force depends really on their mass. That determines the acceleration. So here the question for you is, what's the acceleration of these asteroids? What
And
helps?
I had a
Uh-huh.
question, sorry. Does F equal gravity or
In this case, yes. The force that you have over here is the gravity. In physics, it can be any other force. But in this example, it's the force of gravity.
I see. So, oh, sorry, I cut you off.
But that's okay. We already concluded in the first part, right, that different forces are acting on these asteroids on the left side. This one feels the greatest force. But what
Yeah.
helps you in this problem is that all of these asteroids are the same, right? So they're not like my sun and the sumo wrestler, but they're all basically, let's say, my 4 suns, right? They're all the
Yeah.
same. So that means then the more force you apply, the more acceleration will be resulting, right?
Yes, definitely.
Okay, so that should then, that's it. You don't have to do any calculation over here. You just
Because
have to be able to reason that.
yeah, because it's the same. It's pretty much the same as the gravity,
Mhm.
like force upon it. Like the more force, the more acceleration.
Exactly, because they have the same mass, right?
Yeah.
Good. So
Is that
this
vice
one,
versa though? Like
what
does
do you-
the bigger D asteroid feel the same force or
so this asteroid over here, this chubby
yeah.
one, okay, it's going to, let's say, is going to accelerate. Let's say it feels the same force as this little one, right? But it's going to accelerate less because
Uh
it is more massive. It has more inertia. It has more resistance. So you can see when you're looking at their mass, it has 4 times more mass, okay? So whatever is the acceleration of this one, the one on the left-hand side, this one will accelerate 4 times less because it's 4 times more massive. It has 4 times more resistance to the force that it's applied on it.
yeah, definitely.
Make sense?
Yeah, that makes sense.
Okay, very good.
All right.
Good. I think this is a good pick because that was the one that was harder as well.
Mm-hmm. Um, yeah, sounds good. Everything's good.
Did you have any other question? So I think the other ones were easier, the exercises, 3, 2, and 1. I don't know about worksheet. Did you try the worksheet?
I don't think I did try the worksheet.
Okay, you should try the worksheet. Worksheet is also really good. No, really. And I especially like, this will come on the exam, this will come on the final as well. This picture over here with the earth and the moon, and then some of these questions below also are really important.
All right. Yeah, I'll probably do that later on tonight.
Okay, so if you want, you can do that. And if you want, you can post this on the discussion board and I can and then review that for you. And then everybody else can use that as well if they want.
Oh,
Or
okay.
just like, post questions on the discussion board regarding to these questions. And then I can answer and that can be used then by everybody.
All right, cool. Sounds good.
Okay, very good, Tristan.
Oh, and I don't think the quiz is up yet.
Oh yeah, okay. I'll post it now as soon as we are done.
All right,
There
cool.
will be only one quiz.
Nice.
Okay, good.
All right, thank you. We'll have a good day.
You too. Bye bye.
Bye.